lecture, and today is kind of a brief introduction on an overview of the Abaqus software. And for those who might have had a touch of the software, so this would just be kind of an overview. I'm checking my voice to see whether I'm okay, whether I'm audible from your side. Just a check, a little bit of a check here. You can see I'm unmuted. Okay, I don't know, confirm to me whether you can be able to hear me clearly from your end. And also, my voice good. It's okay, it's okay. Thank you for joining. I can see we are quite a number. And just to start you off, I would like to start by sharing what we have already covered in lesson 1. For those who've been following us, we've been having a lecture series, Introduction to Finite Element Methods. And this is kind of the 7th lecture. And we are kind of coming to a conclusion based on the undergraduate curriculum. But this is not the end. This was just an introduction to finite element methods. So going forward, you have a feel, and then you'll be confident. Now you can be able to tackle even advanced cases of finite element analysis. And whatever you're going to do today is mostly what now you'll be you find like it's applicable, most applicable in the field when we come to the analysis and the softwares. Now, when we talked about this is on page 14 on your notes, lecture 1, types of finite element. We talked of 3 types, general types, 1D, 2D, and 3D types of element. And so far for manual calculation, we kind of concentrated on this category, right? Where we had the spring, we talked of the truss of the bar element, and of course the beam. We did not cover this. And then the beam, we extended combination of beam and 2 beams oriented in an arbitrary plane to get a frame. But you see, even though the element can be oriented in a Cartesian plane, maybe 2D or even in 3D Cartesian plane, but the element by itself is just a line, right? It might have 2 nodes and degrees of freedom per node, maybe for a beam being 2, for a bar being 1, but still 1D line element, right? So in cases now, when we talk of 2D, consider a case of a slab. This is a typical slab, right? And this slab, you want to analyze it using the finite element method. When we are talking of a beam or a frame, like the one in Abaqus documentation, so I believe it's something like this. So we can be able to analyze this as a truss or a frame, plane frame, so that this element, one line, they carry axial load, 1D element, pinned. But when we come to a case for a slab, yeah, and it have got some significant thickness, it's not a thin plate, right? Usually in Kenya, this one ranges between 150 to 200 or 125 to 200. And for this case, to discretize or to do the finite element analysis, of course, the first stage is discretizing. We break it down, we divide it into finite element. So these finite element by themselves, they are not straight line, like we are saying this one box here. Yeah, this, if I can shade this, so this one here, this is one element. Okay, so it's not, it's unlike the case where we had a truss or a kind of a truss or like, let's say a bridge framework, whereby the members can be represented in 1D carrying on the actual, or when we talked of the beam, in this case, for the beam, we are just concerned about, we talked of the degree of freedom here being 2, another one here 2, but this element itself is 1D. It's like a straight line. But now we want to consider a case whereby for a solid beam, right? For a solid beam like that, now you are discretizing or you are subdividing it into different finite elements, right? Not using line element. These now have got the aspect of length, width, and sometimes if it's 3D, thickness. So I took a case of a slab here to illustrate the 2D element. But if we consider for that slab, the thickness is so small here. So we talk of thin plates, such that when you discretize, we can disregard this. Or case of plane strain or plane stress consideration, where the stress, remember this is, they have that direction, we have that direction, and we have the depth direction. But if any of the stress, the principal stresses and the shear stresses, perpendicular to this plane are equal to 0, we end up having a case of what you call plane stress or plane strain, if you are considering stress or strain. So in this case, we use a 2D element so that you have a rectangular, a triangular, what we call the equilateral plane element 2D, which have got this dimension or the direction X, direction Y. So note that initially, or when we are talking of 1D, we would have talked of this boundary being one straight line, another one straight line, another one straight line, another one straight line, being 4 elements. But now in this case, we are saying this is one single element. Because there is a material, there is not a void. Inside here, there is not a void. When we are talking of a single line, it's like this place was a void, like when we have a truss, right? So we're just taking the members and then the middle part is a void. But now this is a plate. So this part is not a void. So we need to, finite element analysis, we want to interpolate. Let's say if it's a plate being heated here, you're applying heat. We want to get what is the heat, the temperature at the midpoint, because there is a material there. So that's why the issue of 1D line element cannot be applicable here. When we now have the thickness, if the thickness is not too small, and also if the principal stresses, either the shear stress or the direct stresses are not equal to 0 in the thickness direction or in all direction, then it means now we have to consider the depth. And that's when now we come to the solid element. And you find this one being so much applicable, more often applicable than even what we studied in the 1D and 2D. But why did we start with 1D line elements? So that we can understand the concepts, manual calculation. Because if you start the student with the just softwares, you know the saying in computation or computers, giggle, garbage in, garbage out. If you just know how to use softwares without knowing what are the concepts or the principles behind, what are the calculations, what are the computations that the software is performing, then you'll just be throwing in whatever you do a good model, but you do not understand the concept, you put long loadings, and even the output that you get, you might not be able to actually comprehend it. So that's why we started with simple 1D line element for computation. When you start coming to 2D and 3D, you may find like manual calculation becomes almost impossible. But of course, you can come for 2D. Now, here I might want to mention something about the 2D plane element. So this is our thin plate. Let's call it a slab with a very thin thickness such that we can disregard, such that the stresses in the thickness direction are almost negligible or 0. So we end up having a case of plane strain or plane stress. So you discretize this using this plane 2D element. Okay. So this element 1, another element 2, another element T. This element have got 4 nodes. Okay, 1 node there, another node there, another node there, another node there. Okay. Now we extract this individual node. This is the one that we have given here in this figure there. Okay. Now in each of the nodes, remember we have disregarded or we have ignored now the thickness direction. We assume it's negligible. So we have this axis, the Y, and the X direction. So per node, we can have, of course, the coordinates will be if this node I, J, K, L. So this one will be, we have the coordinate X, I, Y, I on each node. This is X, J, Y, J like that. And on each node, we can have transformation U, I, V, I. UI is in the X direction, VI is in Y direction. So we have 2 degrees of freedom per node. So for a 2D plane element, we'll have 2, 4, 6, 8 degrees of freedom. 8 degrees of freedom per element. And the element have got 4 nodes. And a special consideration, so this one now tells you when we come to 3D, if you introduce now the thickness direction, it will become a cube, what we call the solid element. Okay. And this solid element have got how many corners, vertices? Is it now? Is it? These are the edges. So how many corners? These are 8. At the in each, because now we are considering that direction, if we consider translation only, then it means we have 3 degrees of freedom per node times 8. So 24 degrees of freedom, not considering rotation. So you can imagine one element have got 24 degrees of freedom, telling you how many, our equation will have how many unknowns? 24. So it will be, the stiffness matrix will be 24 by 24 if we disregard the rotation. So that's why I'm saying now the computation power of the computers now come into play. Now, with this, I don't want to overwhelm you so much because it's just basically an introduction and overview, but I wanted you to appreciate as we move from 1D to 2D why we really need to use the computers, why you really need to install that Abaqus and do this analysis, okay? Now, another thing, maybe let me mention this. We talked of, I have discretized using rectangular plane element, 2D plane element. And if we can also have a plane element having not only 4 but 3, like a triangle. You can make it a triangle. I won't use this term, but maybe it might throw you off a little bit because of node regeneration. When the deformation maybe of when you pull, when you stretch or apply a load to a structure, of course, deformation occurs. And sometimes you may find like this node, it stretches too much, it becomes too long, maybe something like that, such that you almost end up having, there were 3 nodes, but this one comes together to have 2. You had 4 nodes, but now you end up having 3 nodes. So that's one way we can end up having a 3-node plane element. Or you can just discretize. And some of the softwares, some of the software that I've encountered, they like using the triangular element. And the advantage of this triangular element is that we call it a constant strain triangle, or CST. And the constant strain triangle, the strain inside the element is constant. Okay, the strain inside the element is constant. So if we have our plate, not a plate, let's say our thin plate like that, then we discretize like this using triangular, rectangular 2D element. Then maybe let's discretize further, okay, to make them constant strain triangles. Okay. Then, of course, this one you just need to define the geometry in the software, and then start doing computation for you. Now, what we are saying is that for each, the strain here, let's say this is a plate. This is a plate that is fixed on this head. Okay, let me use a different color scheme. This is fixed head, and a load is applied on this. So let's assume there's a plate that is being pulled on this head. So the load is applied. So to get the strain in, maybe you want to get the strain at a certain distance from this X. And let's say this total length is L, and this plate, of course, have got the width as B. So what we are saying is, oh, I see the photo have covered where I'm sketching there, but I can just move it again. So we are saying we have a plate here. This is our plate. We discretize it, right? Like that. And then we are using, now employing the 3-node plane element, what you call the constant strain triangle. And I'm assuming this head is fixed. And then I apply a load on this head, maybe a displacement I pull. So you may want to get, maybe at any distance, at any one point, from this head, this distance X, from any, and the total length here is L. So at any one point, you may want to get what are the strain or the stress distribution, like in terms of contours. So what we are saying is that you need to calculate or to obtain what are the stresses in this element, element 1, element 2, element 3, element 4, like that. And in each of the elements, the strain is constant. We call it the constant strain triangle, right? So that's just an overview. But let's see in application. I believe in the first lecture, in the second lecture, I also gave a little bit of application, where for the 1D case, so for the 1D case, this is just a space frame. So the frame, like a bridge guard, if you look at the other side, if you have a frame structure made of steel, and then maybe a concrete decking on top. So this in itself these lines themselves, they represent a structural member. It could be a strut, could be a tie. Now you can do the direct analysis. For the 2D plane, consider application of 2D plane element. Consider this kind of a structure where the thickness is negligible. And in that case, we have employed, of course, if you can look, zoom in clearly, you can see this rectangular element. So these were typical of plane constant strain triangles. Then in the term of 3D case, this one you can look, it almost looks like a spanner, but it doesn't have the grooves. So this is now the application of 3D cases. So for your assignment, you are going to employ, you are going to employ 1D element. 2D, I thought, let's go to an advanced case. So for the practicals, then we are using the 3D element. And today I want us to give an example, a typical example of how you analyze this in the Abaqus software. Okay. All right. Now, that is that. For that, you can go back to that lecture and refresh. So allow me to just finalize, or to go to now to the work for today. Oh, I had not noticed who had commented here. And Teresa and Tere, thank you for coming in. I hope this might be a bit off for you, but I know you're also in education. And Teresa is my fellow colleague on YouTube, and she is doing a very good work with the high school student on chemistry practical. So you might consider checking out her YouTube channel and what she is doing. All right. So let me stop sharing that. I want to share my screen so that we can be able to see what I'm talking about here. So now, let me share what did I want to give the assignment. So from here, I can share the screen. Okay, good. So if you have any question, kindly, as usual, leave it in the comment section. If you have a question later on after the live stream, you can always leave it in the comment, and then we can address it later on. I know you've started with this assignment, so I've just projected it there. So this is what I was saying. The first part, where we are talking of the case, you have two-part assignment. This is your continuous assessment. The first part, where we are given for the case of the overhead joist given in Abaqus documentation. So somebody was saying this one is not available, but I said install the Abaqus student version. It's free. The Abaqus commercial version is over 1 million Kenya shillings. So for a student, it might be difficult to have it. So use the Abaqus student version because we want to have a film, or we are studying. We are studying, and I believe once you get into touch or the field using the student version can do everything. The only limitation is the number of nodes. You can only do an element with maximum of 1,000 nodes. Yeah, so you may not be able to refine the mesh. Remember, we said the more you refine the mesh, the more you get closer to the actual answer. But of course, there is a limit up to which, even if you continue refining the mesh, the solution does not, or the answer does not improve. Okay. Now, for those who have started on these, there is a getting started with Abaqus, a Simulus tutorial. These are the owners of Abaqus, so it's a very good tutorial that you can click also watch. I gave that. And then, so in this assessment, let's first see where you get it. So one thing that you have to note is, I'm assuming you have installed the Abaqus student version, right? And if you have not, in this, I have given the link where you can be able to obtain Abaqus Student Edition. I don't know whether it can open up faster. I believe my internet should be fast enough. Or you just type Abaqus Student Version. So you can take this link there. So this is where you are supposed to come and, sorry for that, I'm not annotating. This is where you are supposed to come and download for free. And you can take this link there, okay? Or you just Google, you type Abaqus Student Edition. So download this one for free. Once you download, it will come with the option of documentation. Abaqus have got its own tutorial. So there will be documentation. Now I have installed in my computer, and this one I think I did it 2019 before Corona, so it's an older version. But for you, if you download, maybe you get 2021. So when you come now to your installed softwares, Abaqus is by the Dassault systems. So you just come here. You see the Dassault system. This is where Abaqus is installed, of course. We have documentation, software management. We have the second part folder is Abaqus CAE. CAE is complete Abaqus environment. Now you come to understand there are different parts or types of Abaqus. You can conduct Abaqus by coding, writing Python scripts. You don't have to see the graphical user interface. But this one, CAE, it's called complete Abaqus environment. It have got the modeling part, like you use it the way you use the AutoCAD, you have the graphical user interface. Then you also have the analysis stage, and then you have the visualization stage. So Abaqus viewer is only visualization stage. After you have done your analysis, to view the result, this is what it does. Now, Abaqus command is like where you issue command. And this one, I know you know how to use the CMD. Just come and type there CMD in your one, and then you can be able to do a lot of things here. It's kind of a belief of coding. I mean, for those people who are hard in coding, they find it very useful. You can be able almost to navigate in your computer, even in Word, using this kind of the command prompt in Word. So here, this is what I had given, or I'm showing here in terms of Abaqus. CAE have got everything. So basically, you should be coming here and clicking CAE to be able to launch Abaqus for your modeling. Now, as you can see, this is the student version. But for me, I have got the licensed version here. But it's very old, 6.13. I think now you're almost 2021. So, but this one I can be able to do without being limited. Now, once you install this Abaqus, you're going to find, like in Dassault, the folders that will come, assuming that you did not opt out, you're going to get documentation. I mean, sorry, in system, you're going to see Abaqus documentation. This is where you can get your tutorials. Saina Kim's, this tutorial comes in handy in our final year project. Sir, thank you so much, Kimeli. Oh, good. So now, documentation in itself, you can study a lot. I'm saying there are a lot of tutorials there that you can be able to get a feel, or to get the theory behind, and also if you want to understand different concepts. So Abaqus documentation is your first teacher. Even before you go to YouTube videos, this is your teacher. We still come here even after we have used them and analyzed many structures. You still come here and we want to read more because it's diverse. All right. Now, if you click Abaqus documentation to open, this is something else I also noted with this. You're going to get to this page, but nothing will display. I realized that for you to get this documentation, you need to set your browser to Microsoft Internet Explorer. So I'll briefly come here, and then I say default browser. Now I'm in my computer, you are seeing my screen, default browser. So I set my default browser to Internet Explorer. So now for me, I use Firefox. So I will set it briefly to Internet Explorer, right? So with that, I can come again and launch. I come to documentation. Remember, you can also use this command prompt here. I just say Abaqus documentation. You see it comes here. I can search it. So I launch it. I have launched it. And now here at the bottom, you see there is allow blocked content. So with allowing block content, now I can be able to see the documentation. Now, for that student, there's one student who was saying that whatever I have given as an assignment is not here. So it's there. It's there. What you need to do is that maybe you are not able to access this documentation. If it was the issue with your browser, so now you are on the no. Now, once you come here, to get that problem for our assignment, you click Abaqus, you expand. Then you come to getting started with Abaqus. Then you come to Abaqus basics. Then you get to example. You see this example here, overhead joist. And in the first case, you are given what is going to be covered. The second one is this. So this is the overhead joist, hoist, not joist, hoist. Yeah, like if you go to our structures lab in Jomo Kenyatta University structures lab, you have that crane that is moving on the roof. So there is a setup. There is a hoist that is holding that crane. So maybe you may think of it like this is the crane, the 10 kilonewton. This is the crane moving along this this rail, and this is now the hoist hosting the overhead hoist supporting that crane. So we are to do this analysis. So the first stage in your assignment was any method, use any method that you learned in previous theory of structures. So maybe method of resolution at the joint, method of graphical methods, or any other method, because we want to see how do they compare, how do they relate between the finite element method, using the software, using manual calculation, how do they compare? So you use that method, that's a part A. Part B, now you manually calculate. So part B, you manually calculate using what we have studied, finite element analysis. You calculated. You see, we have how many elements? It'll be 1, 2, 3, 4, 5, 6, 7. And is it symmetrical? Think about it. If it's symmetrical, you can apply special boundary condition, and then you can be able to mirror. So this you should be able to handle manually in a very easy manner. You are given the diameter, so which means you can be able to get the area. Remember, for the bar, you just need A. K is equals to A of L, 1 minus 1 minus 1, 1. Right? What do I mean? For those people maybe who might have forgotten briefly, let me just say, this is what I'm saying. The stiffness matrix for the bar element is AE over L, 1 minus 1 minus 1, 1. Right? So the area will be given by the diameter. The stiffness, not the stiffness, the modulus is given here. This is still 200 gigapascals. You are given the density, you are given the Poisson's ratio. Remember, we said for the stiffness, we need the material characteristic and the constitutive material model for the finite element analysis. And then you are given the procedures that you follow. These are the typical procedures for finite element analysis. Any modeling in Abaqus, you have to define the geometry. You sketch your geometry, you give the material property, you have to assemble. Now you have to set your analysis, you apply the loads and boundary condition, you mesh or discretize, you break down, then you create that job which you are going to do the analysis in Abaqus. And after the analysis is done, you're able to view the result. Sometimes depending on the number of nodes, like we used to analyze in my PhD, I used to analyze a model which could run for almost 4 days. There were people who are running models learning for over 2 weeks. But in that case, you cannot use your normal computer. So there was a supercomputer. You know, now in Japan, facilities is not a limitation. So there was a supercomputer in a central location. So in your analysis, you are just doing the modeling, and then you can set that work for analysis. A very powerful computer. If you do it, there's a model. If you model, the nodes are too, like now I have a software which is a licensed version. If I model, even if I have that capability, but my computer is limited, right? If I define so many nodes and a very big model, it will become too heavy and my computer will hang, will not be able to run the analysis. Okay, so for your other part of the assignment, the part 3, numerical simulation using Abaqus CAE, this is very easy because you are just going to follow this tutorial. It's already done for you. Yeah, it's already done for you how the part was created, how the part was created, how the material is created. So follow these steps until the end here. So this example creating hoist, all these steps from here, all this stuff to here, you'll be able to cover that part. So you can see it's very easy. It's like kind of for your analysis, for your assessment, I'm just giving you some free bonuses. Because for me, I believe more in understanding than in the examination. Of course, you have to pass. You need to pass. And on this note, for the JQual student, the graduate, I know this platform, many people come and they watch later on. But for the graduate student in 4th year, your exam starts on that next week on 9th. So you need to pass. But of course, don't worry. My exam is usually the easiest. Yeah. So I hear. All right. So in the practical assessment now, this is now where we are having the 3D finite elements, 3D elements, and I have subdivided you into groups. So the class is about 170. So I think 163 those who appeared for the CAT. So I'm assuming 170. So divided into groups of 7, you are expected to have how many groups? Around 35 groups. So that was my rationale. So I'm saying group 1 to 7. I don't know how you label yourself, whether you are group 1 or 2 or 3 like that. Group 1 to 7, you do a steel column, whole section, and a compression. Then, under this analysis, these examples, they have been done in YouTube. But now I want you to understand. I want you to do the analysis, the actual analysis using Abaqus software. And that's why I said, I just don't want the report. I also want you to send me the model so that I can be able to see the work that you have done. So the second group will do a concrete beam at a 4-point bedding. So this is like you're going to confirm what we learned or what we do in the experiment. Usually we do, when we are testing the fracture, we do a 4-point bedding, right? When you apply the 2 loads there, or you can apply a center point load, then you are going kind of to confirm that theory using the finite element method. Another person to do a concrete column, and in this case, I'm assuming maybe you can remove the reinforcement. So this will be kind of like a concrete cube crashing. Then another group to do steel plate at a compression, and another one a steel plate or a reinforcement bar. Why I gave these 2 examples is because I want to use one as an illustration. So if I do rebar, this group you're supposed to do plate. If I do a plate, then you should do the rebar. Okay. So I think now you understand what is expected of this assignment. The deadline for submission, assignment should be 6th August. This is the last Friday before you start the exams. Because the exams start on Monday 9th. So that Friday, you submit the first part of the assignment through your class labs. Yeah. And it should be submitted as one set. So I don't want you to come later on and say, I want to submit, And maybe I should mention here, take the assignment carefully, because 4th year is very critical. You cannot carry any baggage to 5th year. As small as missing an assignment, you end up not proceeding to 5th year. It's unfortunate. So I don't want that. So take this assessment carefully, seriously. Then for the practical exercise, I've given you, I think this is the maximum time, because I believe Friday 27th August is the last Friday of the semester. So by the time you are leaving, this is when you are to submit this. So you prepare a short report, and also you submit a soft copy of the numerical model in a CD. Why? Is because I want a soft copy to see the model. Now I don't want to tell you to submit via my email, because now I'll have so many segments. Like people submitting this day, they say the email did not come. So now burn it in a CD. I know it, I believe in technology, and I try to move faster with technology. So you should be using Google Drive. But again, the number of students that we are dealing with, there are many, very many. I don't want to miss any one of you. So that's why I opted for a CD. So in the CD, you just like the registration number of both of you. All right. That's not with the assignment. And let's start with one example. And I want to do this tensile test of a steel plate. Please confirm if the assignment is, no, it's for group. It's for group. Yeah. Thank you, Humphreys. So the same groups that you are working with, because again, if you give me 170 assignments, and I'm marking 170 cards already, I've not started, and the exam is coming 170 times 3 questions. It's too much work. So work as a group. Okay. All right. That's that. So let's start with a first example. So I just come here. For me, I was saying you can use the command prompt. You can type a command prompt and then you open Abaqus CAE. You can search here Abaqus CAE. You can search here Abaqus CAE. Or you can just come to the folder where we saw dashboard systems, Simuria, Abaqus, you open Abaqus CAE. Okay. So it's opening. I believe it takes a little bit of time based on depending on the internet connectivity. No, not the internet, the computer. And I believe I have a little bit advanced computer, although I want to upgrade. This is a Core i7 with 1 terabyte of storage and a speed of 3 point something gigahertz. Sorry, let me close here so that you can see how I have opened again. Just come, you open Simuria CAE. Let's wait. There's a step I want you to see. This part. Once you open, you're going to get this part, start session. In the start session, we have create model with standard or explicit model. So let's go with the standard. With the electromagnetic, you are not dealing with electromagnetics. If you have an older model that you have created before, now you're going to create the first model today. So an older model, you can be able to open it using open database. Now, if you have prepared a Python script, you have prepared a program in Python, then you can be able to run that script so that you do the analysis. Again, this is a stage 4 tutorial. So when you have your time, you can click start tutorial. You're going to see the different examples that have been worked by Abaqus. So to go direct to our modeling, we go with standard. Standard explicit usually is for dynamic analysis. Standard, you can do linear and nonlinear analysis. Now, once you are here in Abaqus, this is the graphical user interface. So we have the viewport, this area in black. We have the menu bar here on top, the toolbar. We have the tools here. This is like a short, just like a way in AutoCAD, you have the tools, the icon. Some of them represented by the same command can be issued from this area. Now, this is what you call the model tree here. And this area is arranged in a way you are going to execute your modeling. Remember the same way we said for finite element analysis, we start with selecting the element type, you discretize. Like there was a certain procedure for all the examples that we covered. Even here in modeling, like parts, you create the model. So you create different parts. Then you have to define the material for different parts. Maybe you have a composite structure, where maybe a concrete, a concrete the steel decking. So you have to define for different parts what are the material. Now for the different section, you have to define a section like steel section, you have the concrete section, and then assembly is when now you have to bring together to make the structures work as one. Remember, if they are just separate, there will be two separate entities. You might draw them close to one another, but unless you define that they are one entity, they will not act together as a structure. Then, of course, defining the steps of analysis. Sometimes for today work, maybe you're going to just have one step or two steps. That's a step of boundary condition and applying the load. But you may find like later on as you advance, you may require different steps of analysis. Like there is something happening, and then at a certain point, a certain load is applied or is removed, or another part comes into play. Like let's say you want to study the corrosion or the impact on a building. So there is a building that is static, and then there is a load that is coming to hit on the wall, on the structure. So there is the motion that's coming. Maybe you want to analyze the static building before the dynamic analysis. So there will be another step that you define when the contact comes into play. But for today, let's keep it simple, bare minimum. What does it entail? So your analysis, you learn from defining parts, all the steps, then you request the output, you run the jobs analysis job here, and then you are going to be able to view your result in different areas. So when you look at Abaqus, it looks like most of the software that you have been using. I know now at fourth year, like AutoCAD, like ArchiCAD, you are used to this. You are not now here bombarded by these icons. So they are not even very many like the way we have in AutoCAD. All right. So the first stage is we need to create a part. So I'm just going to, is the assignment hard written? Huh. Why is that so? I don't know. I want to leave this freedom to you. The only thing I don't want to see, because I'm really serious on this. Last year there was a person who just photocopied an assignment and changed the name. In that case, for sure, even if I'm sympathetic with you and I know you have spent school fees all the way to fourth year, in that case, that allowance, you don't go to third year. Yeah. So sometimes I know some lecturers say have a hard written work so that you do not just change the work of somebody else and edit. But for me, I believe we should go past that to the understanding, right? So if you want to do hard written, if you want to do a good typed work, well and good, but let it be your own work. This is for your own good anyway, for future. All right. Then, so let's start. So I'm just going to have a plate. I fix it on one edge, and I apply a load on the other, and we conduct the analysis. So what I come here, I do is that I start with the part I want to define the geometry. So first things first, part, let me call this plate. It will be 3D, it will be deformable, it will be solid, and I want to use extrusion. So at this stage, let's maintain things as default as possible. Maybe I can explain what they mean. Later on, as you advance, you're going to see where you can use other type like 2D planner. If we are talking of 2D element, I would have gone for 2D planner. Axisymmetry is when like something rotating in an axis. So I want a 3D plate which can be able to deform. Sometimes we want to have a rigid part. Like when you are doing the 4-point loading, remember the load application point. Those if you are in the lab, we will talk of the hydraulic jacks. The one that are applying, you don't want that to deform. When you are doing the test in the lab, maybe a concrete compression test. Why we use steel plate? Number one is to create a flat surface. Number two, we don't want that steel plate to deform. So in analysis, we use it as a discrete, rigid. You're not going to deform. Now, shape, how are we going to develop the base feature, or how are we going to develop our structure? So I'm going to create a plan and then extrude. Sometimes if it's conical or it's round, I may choose to create a part and then I want it to sweep around. So maintain the default for now. So I say 3D, deformable, extrusion, approximate size. Let's just keep that. I say continue. So this one now creates for me the drawing canvas, the drawing area. And now you see now the tools have changed. Every time you select a certain module, like when I move from part, I go to the material, these tools change. So here is just drawing like the way you draw in AutoCAD. So let's say I want a plate of this kind of, I want a plate of this thickness. Yeah, I want a plate that thick. So that's it. And if I want to dimension this, I want to see what are the dimensions. Okay. So you can even delete. You can delete your structure. You just need to click on it. So I know you might not be it's not a very good way of teaching this, because you should also be on your computer doing what I'm doing. So I will try to move faster, but I wanted you so that as you start in your assignment, in your practicals, you have a feel of, so that you are not stuck in one area, you'll be able to move faster. So the other kind of practice you are going to do, this one you can do later on your own. So I've just created that. I say this is my thickness, and then I want to protrude that. So I say done. Then I want to have a length, a plate of a length of, let's say 100. So that's my plate. Okay. So you see, I just created this part. I just created this. Then this one I did extrusion, the length. Okay. Now with this, I have created the part. I want to define, let's do steel. Okay. I want to define material. So because I have finished with the geometry, let me do material. I want to define material. So I double click materials. I say I want steel. Okay. Then general, you might define density. You might define regularization. Density. I have never even used regularization, but you can define the density. Now, what you need to know is that before you come to numerical analysis, you need some data from experiment. That's why a numerical model, first we need to validate it from experimental data. So you needed to have taken a sample test of a steel plate and gone to the lab in the tensile machine. Then you do a tensile test. You get the constitutive material model. Now the constitutive material model, you are going to get, let's assume it's mild steel. You're going to get something like this. Mild steel is something like this, is it? I know you remember this curve, where this is stress, this is strain. Now with that, we have from 0 up to elastic limit here. Of course, the modulus is constant, E. And usually E for mild steel is around 200 to 210 GPa. Okay. Then because of when you are getting or compressing, we have the lateral deformation. Usually we define Poisson's ratio. Now, if I was in the lab, I have this data, so I'll be having this point. If I gotten this point from using the strain gauge, I'll have this point. So I can be able to define both the elastic part and the plastic part. So I can be able to come and input material model. So I'll have this data in terms of a table. Yeah. From the experiment, you are going to have stress and strain. So from 0, 0, of course, it's at the beginning. So at this point, let's say at 350, that's my yielding. Maybe the strain is 0.2%. Okay. Or 0.002. Of course, you don't write in percentages. Then maybe this is the yield plateau here. So still at 350, I can have the erogation coming to 0.8%. Then here I may have different values. Okay. But now, because I have not gone to the lab, I'm just going to assume elastic plastic material behavior. That is, after yielding, it becomes perfectly plastic. No strain hardening. Strain hardening is one that that enables here now the load to the stress more to carry more load even after the yielding. So usually, if you don't have this data and you know the typical, you know, in your assignment here, I have said in your assignment that did I make that one clear? Yeah. Assume reasonable material properties, geometry, boundary condition, and any other necessary information, and make sure to define it in your report. So I believe if there is a group that is doing a steel column, right? And this group, a hollow section, let's say one group is doing a RHS, rectangular hollow section. Remember, it's hollow, so it means we should be able to see like something like that. So, and then this length is, let's say you are taking of 1.5 meters or something like that. And the dimension here you have defined maybe is 200 by 200. I don't expect another group to have this, right? We could have another group to have a circular hull section, or even if it's still going to do with the rectangular hull section, this measurement, you're not thinking the same. This measurement should be different, right? So assume reasonable material properties. Materials could be the same, because if you choose mild steel, I use the word reasonable because you already covered in strength of materials. You've done some typical experiment, like you know the typical, like now I'm already telling you for mild steel, E is between 200 and 210 GPa. Yeah. And the Poisson's ratio is usually, I think, in the range of 0.3. Okay. 0.25 to 0.3. So from even literature and from books, you can read even paper. If you want to use high yield steel, just get a reference and then get what are the typical material characteristic. And then I was saying in my explanation here that the material you have not done in the experiment, so you might not be so much detailed enough. So if you assume elastic, perfect plastic, so that you can be able to model plastic behavior. In my analysis here for our experiment, I want us to concentrate on elastic analysis, right? So I just want to have I just want to define what is the Young's modulus. So I'm assuming that my structure will not deform plastically. My material will continue behaving in a linear manner indefinitely. So I just need to define E, and of course, because of direction, I need to define the Young's modulus. Okay. So with that, so this is why I had come here and said, you come to mechanical, I want to do an elastic analysis. You define the elastic, isotropic. Isotropic, we say that the behavior, the material is homogeneous in all direction. So the Young's modulus 210,000 MPa. The Poisson's ratio 0.3. I said, okay, if I wanted to do elastic plastic analysis, what you call elastoplastic analysis. So I would have come now to define again plastic material behavior. I would have now to define the yield stress. So what I'm doing here is elastic, plastic. So I need to define at what part, whatever I'll define here, the yield stress. If the yield stress maybe something like 0.0, maybe 0.002, because it's 0.2%, let's say. Sorry. That should be on the strain, 0.002. Then on the stress, maybe my material is yielding at around 350 megapascal. So this one I would say 350. Okay. And then I want to analyze until this head. Remember, Abaqus is an ideal platform. It's like we are in the real world, and now we have taken our structure to an ideal platform inside here. So if you do not define the limit when it's going to fail, or you're going to do your analysis, the structure may continue deforming indefinitely. So in this case, maybe you say at this stress, at the same stress of 350, you want to define the stress here maybe at 10%. So maybe 0.1. So you have now, with that, I have defined both the elastic. Remember, in the elastic, mechanical elastic, I defined the Young's modulus, so I'm able to get the behavior here. And now in the elastic plastic range, I've been able to define what is the yield stress and what is the behavior here. If I had the actual material characteristics from the lab, that after here, I know how it's going to behave. So I'll have this data. So I'll have this data. That means this data, I have it. So I'll just come here and I press enter. So I can be able to enter actual data. Let's say I have yield stress of 350 at this part, 350, 0.02, maybe at 350, that's a yield plateau. It's yield up to 0.08, 8%. Then I start increasing 365. So this is from the experiment. You have this data from the experiment. So that now I start defining this part. I start defining this part. So for us here now, for our analysis, we do not have experimental data. So assuming, if you can be able to assume reasonable yield stress and the yield strain, then we, and I mean, not yield stress actually, because it will continue, it's not going to yield, right? So it's going to behave in, or to obey Hooke's law indefinitely for my analysis here. So in this case now, I just need to define the plastic rate, the elastic rate. So in this case, this part I can disregard. I just need to delete that. I just need to define the elastic material, the one I defined, and I say, okay, this material is steel. Description, you can write something. This now helps you to understand in the future, like, why did you do that? Because you may have different material. So you may say this is mild steel. You may assume this is mild steel. So we have defined the material. There's an error. Tabular data for at least one portion has either blank or zero values. Oh, this mechanical plastic. Oh, this data is reading 0. So let's cancel here. Let's create the material again. Let's say this is steel. This is mild steel. You don't have to write here mild steel, but if you do not, for documentation in the future, you might not understand. And then we come to mechanical elastic. I just need to define Young's modulus of 210 GPa or 210,000 MPa. Then this is 0.3. Remember, this one will depend with the units. And when you are going to look at the example in the documentation for the overhead hoist, it shows how the units can be set. You can set your default unit. Because Abaqus uses absolute values. Yeah? Either you want to use feet, you want to use inches, but consistency, right? So with that, we say, okay. So we have created the material. So we came from parts. Now we have created a material steel. This material is just created and it's there in Abaqus, it's defined. And then we have created this part. So this part and the material are not related for now. So that's the stage that we are in. You need to harmonize them. So in this case now we come to section. We create a section. Now remember, you can use it here. Remember again, another way when I'm creating on the creating the part, or when I'm moving downwards in the model tree. Yeah, this is what I call the model tree. This is the model tree here. This part. I can still come here and click downward here and select the part, the section I want to go to. Okay. So right. So I'm saying I can still come here and I want to go to part. I can come here in a drop down menu. I can come to properties. I can come to the other part. I don't want to click the other part because you might be lost. Now, so far you have covered the part and the property. So the part, we have defined the geometry, and the materials, we have defined steel. Then I want to create this a section. I define this as a section so that I can assign this material property to a certain section. Why do we create a section? Assume you have different parts. Yeah, like you have, let's say this is how can I explain to you? Let's say this is T-bar, and then you are going to have to create a, you want to create to make a table where the legs are made of steel. So I've used a typical example. You have seen table with this, maybe steel legs, something like that. So you for this case, this part, this is a section, with different material property than this section. This is steel, but this is steel. So we need to define section. We say this is section 1. We can call it a plate or a table, or whatever you want to name it. And then we can assign the material. We need to create another material here, if it's steel bar or elastic characteristic. Elastic, plastic, whatever material you want to define. And then we need to assign that this part have got this material characteristic. So that's the purpose of creating section, so that you don't, you're not surprised that why are we creating a section while it's only one section here? It's because in the future you will not only be dealing with one section. So we come here in the section. So you can also see here, if you create here, you can see create material, and you can manage your material property. Still, you can edit if you wanted to edit it. This is what we have already done. So for this, we create a section. I want to create a section. This section, I want to call it, our model, I have called it a plate. So this section, I can call it, what do I call it? Because again, if I use the same name, it looks cliche. Eh? But let me call it a plate section. Okay. It's solid and homogeneous. So you're using solid element and it's homogeneous. The material properties are the same. So I've created that. And it will have, this section I'm creating, it will have the material steel. So that's done. So I have created, if you come here in the section, I have created a plate section having the properties that we have defined. But now we have this part that we created, we call it plate. I have a plate section. I have defined a certain plate section having a certain material property, but they are not related. So I want now to bring them together. And this is why we say, we come here, still on the property, on the section. Remember, you're on this property section. We want to assign the section. The section that we have created, we want to assign it to a certain part. So you double click, or not double click, you click once, and they're saying, select the regions. So if I had different parts that I wanted to assign that material property, then I would have clicked that part. But now, of course, this is just one part. So I'm going to select the whole of it. And then I say done. Something that you have seen I have done here, this one is usually highlighted, the issue of creating sets. For now, I want you to remove it so that you don't end up having so many things here. Sets are very important, but again, creating arbitrary sets, I find it not useful. Okay, so in this case, I have selected the region, so I just highlighted and I say, okay. So this, it means I have picked a region, a section, plate section. It will be assigned this material characteristic, which is solid, homogeneous state. Say okay. So now, this plate that you are seeing is, we can call it steel. Initially, it was just, you are just seeing a geometry. You are just seeing a geometry of a rectangular part. It could have been timber, it could have been plastic, it can be polymer. But now we have defined materials, we have defined the section, and we have said that section with that material is this part. If we had another section, we could say this section with this material is the part 2, right? So, and once you assign the materials, the color changes, the color scheme changes here. Now, another thing, we said Abaqus, we are in an ideal environment, and we need to define something. Remember something I mentioned about rigid body movement. If we try it, like this plate is just floating in the Abaqus environment, inside there, in that environment, like in the world, it's floating in space. So we need to apply constraint. You can apply constraint now, you can apply later. You can do meshing now, you can do later. But I prefer you move in the steps downwards, the way it's listed here in the model tree. So we need to do the assembly. Why the assembly now? We only have one structure. But once we discretize it, remember it will have many elements. Now in that case, this element, when the Abaqus software does the stiffness, elemental stiffness matrix, it also need to assemble together, bring together the whole structure to have the global stiffness matrix, and of course, complete the analysis for a structure. Again, if we had different parts, like if this was a tabletop, and then we have other parts representing the stands. We need to assemble that together, to tie them together. For this case, you might not be able to see the essence of this assembly, but that's the purpose. So because what we just do when we come to assembly, we need to create an instance. We say this is one instance. So we double click an instance, and then we say this is a part, this part, dependent mesh, apply. Okay. Okay, we need to select the part. Select the part. So I select plate. If I had many parts, maybe I had plate, I had stools, I had the stand, I could have selected a number of them here and made them one, if they are one instant in assembly. I said apply. Okay. Okay. Sorry, now here it's saying mesh dependent on part. Okay. If you look, you have to be careful because we have made so many of them. So you need to delete which you just need one instance. If you don't do this, like when you come to the analysis, you're going to have, so you see that's our instance. So it's like it's working together as one instance, and assembly, we have defined that assembly of our structure. So now moving that, there are other parts we call features. Now, in Abaqus, we can have services, we can have geometry nodes, edges, like that. But for now, just so that you are not lost, I want to define two areas. I'm going to apply to fix this edge. I want to fix this edge. Remember, you can use this label, this icon here to rotate. So I want to fix this edge, and I want to apply loading on this edge. Okay. So so that I know how I'm going to define this to apply, I'm going to define this edge geometry and the other edge there. I'm going to create a set. And in that set, so that I can be able to say, on this face is where I'm applying the load, not anywhere else. I'm applied on this part. So that's the part I'm coming here on features. I'm coming here on features, and I want to do what? So this is what I'm saying. I want to apply to define this edge. The edge here I want to fix. This edge I want to apply load. So that being the case, so let me define two features. I want to define a set. Set one, I want to call it edge one. I continue. This edge one I select is this. Say done. Then I also want to create another set, edge two. You can use any word. Continue. So you can rotate here. I click this edge two. Done. So I know edge one I'm going to fix, edge two I'm going to pull or to apply a load. Later on, you come to the areas of services in the future and all that, and how to connect using ties, multi-point constraints. Sometimes use ties. Okay. So for now, let's stop there. Let's stop there for now. Then let me define the steps. The initial step, the initial step is our structure is in place. Then the next step will be apply load. So in this step, the initial, I want to define the boundary condition. This boundary condition, I want to boundary condition one, I can say fixed. It will be a mechanical. Of course, you are not in electrical or magnetic. Mechanical, and I want to encast, fix it, built in on this edge. Okay. So what we are doing is kind of, this is fixed. And then this is our plate there. I'm showing the thickness direction and then a load pulling there. So for you to understand clearly, usually the plate will be maybe on this direction. And then a load is applied here. So this is fixed. So this is why I'm using this option. Encast or fixed edge. If you had the issue of like pinned, you go to the issue of displacement, you fixed one displacement component. Remember in Abaqus, we have this triad here, this axis, coordinate. Now in this coordinate, you can see we have y upward, x in this direction, and z. And the rotation will be u1 is in the x direction, u2 is in the y direction, u3 is in the z direction. For the case when we have rotation, you have ur1, rotation 1, then you have ur2 and ur3. Okay. So in that case now, let's do one. Let's let's define this boundary condition. Fixed. Oh yeah, I was rotating so that I can fix this head. So fixed, mechanical, and cast. And in that case now, somebody calling me here. No, I noticed some people note that I'm in class and then they call. Okay, so continue. When you continue, it's saying select the region for the boundary. So I can come and say I want to apply it on set. I can click here, or I can just say apply it on set. So I want to apply on set 1. And I want it to highlight where I have applied. So I say continue. It's saying the data set is not complete. Okay. Data are not complete. Let's see. Let's repeat it again. Boundary condition. Let's say this is fixed head. Then in the initial step, I continue. Assume I select this part. Continue. I say this is fixed. So this is the encast. You see the pinned. You can define pinned. You can define pinned. You can define fixed. Fixed, you see U1, U2, U3, all these are fixed. There are no rotation or no translation or rotation is around. So it's totally fixed. Here is pinned, so rotation is around. Now this one, these are asymmetrical. And that's why in Abaqus, you find like when you have a very big model, sometimes we use the principle or the concept of symmetry. We just model a small portion. Like in, I remember I was modeling an eighth. There's time I was modeling an eighth of one model so that I could have more refined mesh and my model still remains lighter. So I say fixed and I say, okay. So as you can see here, now our plate is fixed completely on this head. They have been fixed. So if I can go back to initial orientation, this head is fixed against rotation or translation. Now on this head, on this other head now, I want to apply the load. There are a number of ways you can apply load here. You can use force, you can pull, but this is my theoretical case. So in the step, I have step 1, it has been defined. So I want to define another step. Step 1 was initial, it comes automatically. That's why we have to apply the boundary condition the first one. So I want to define another step. Step 2, this is apply load. I'm just calling it apply load. It will come after the initial step. General, statics, general, just continue. Let's maintain that one because we are doing static analysis. No, we are not in heat or soils. So continue. Then let's maintain that one for now. I know these are the number of increments for now. They might be difficult for you to comprehend, but later on we are going to see how they help in refining your analysis. So let that be fixed. Let me just call it tensile loading. Saying okay. So in the apply load, there I want to define boundary condition. In the boundary condition, in the apply load, I want to define another step, boundary condition 2. This is the free end. The step is apply load. Again, as symmetry, but I want to say displacement. Because in my case, I want to assume that I'm going to pull this head. So I'm going to pull with a certain magnitude. And because that force I don't know it, I don't have it for now. So I'm just going to say, you can assume a force, but let's use what you call displacement controlled type of loading. You'll find it's very, very important. You'll find it later on. It's very, very important. So in this case now, I just come here, I say displacement rotation, continue. I'm going to apply it on head 2. I continue. And then you see head 2 is in the direction of Z axis is where I want to apply a displacement. So U3, let's say I apply 20 millimeter. So I have applied a pull. I have pulled. Yeah, I have applied a pull on this head. I have pulled on this head, and this head is fixed. Remember, if I had not applied the boundary condition on this head and then pulled, this structure will be floating on space. So I will talk of rigid body motion. So no deformation will occur. You cannot be able to obtain the deformation or any stress or strain or even the reaction. That's why we need to define the boundaries very well and the displacement here. Now with that, we have our structure. This is like the problem that you're usually given in a typical manual calculation. A structure, boundary condition is defined. The loading on maybe one head is given. In this case, we are defining it in terms of a pool. Okay. And with that, to do the analysis, so you usually start, once you are given here, you usually start with, you choose what type of element you want to use, and then you discretize. So we are at that stage. All the other stages we are doing was like defining the geometry, the boundary condition, material property. Now we have come to the finite element analysis proper. So this is geometry creation, modeling. Now, here, with that, so we need to come to the meshing stage. Okay, so we come to the mesh stage. But maybe before we even mesh, okay, let's mesh so that we can move together. So at the meshing stage, you can come here, select mesh. You see after load, we have the mesh. All right, or even here, sometimes when you are finished with a certain step, you can minimize it so that you can be able to see clearly. So you see, you have come to step, field, then output here, the assembly, all that. So when you are done with the assembly, the load, we come to mesh. Mesh, here is where you say assign mesh control. You want to define model, we do in part. We assign mesh, structured mesh. Okay, this one, let's maintain them as a default. You're going to see when we need different types of like bottom-up meshing. This is in advanced cases. Today is just an introduction. So you want to have a hexagonal, hex-dominated. As much as possible, when you generate our element, we want them to be as rectangular or as square as possible. So we say hex, or you can say hex-dominated, etc. So let's remain with hex. Hex-dominated meaning if our structure was changing in geometry, there are areas where we not have a kind of rectangular or six-sided solid element. So for us, because this is just a rectangle, let's have all of them hexagonal. Okay. Then we come to the mesh. Then we come to assign mesh type. Okay. Mesh type. So we said we are going to do with solid. Geometric order is linear. Linear, there is a lot of learning here. If you remember when we talked of shape function, right? We talked of a solid, node. Then we talked of the shape function being, this is N1, N2. straight line, N2. If you bring them together, of course. And we said they are linearly varying in case of the bar, linearly varying. When we came to the beam, you found that they were varying they were cubic. Okay. In a similar manner, for this solid element, remember we are talking of an element like this. For this solid element, and this side we have the shape function. So if the node is just located there and there, there and there, right? Remember the shape function, basically we talk of, they are expressed in time, they are polynomials. So if it's quadratic, you have cubic expression. So it's like on a straight line, we introduce a middle node. We introduce a mid node so that the deformation will be kind of cubic, quadratic like that, or it can even be cubic. I don't want to make you lost. I don't want you to get lost here. So let's go with the standard. And remember all these, this information is in Abaqus documentation. You can look at it. So we are in standard analysis, linear, 3D, of course, solid element. The other, let's remain like that. Reduce the digression and all that. Let's this be remain a default. And then we say, okay. Okay. So now we need to mesh. Remember, you can also even use up here for meshing. To mesh, first you might want to see how are your, you might want to see how are your, where will your element be? How are you going to subdivide or discretize your structure? So you can say seed edge or seed part. If you seed part, let's assume you want a size of 5. You say apply. So this is where your nodes will be. So you can imagine how your structure will look like. So if you say, okay, then I can come here and say mesh part. Mesh part. Yes. So we have meshed our structure with rectangle. Now this is one element. Sorry. This is one element, one solid element, another one. So you have how many elements? 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. 20 times 9. You see 180 elements already. You may want to query. You come to tools, you want to query how many nodes do you have? Element or node. I say I want to know how many nodes I have. I highlight the whole of it. So it's going to give me all the nodes. I wanted you to see it here at the bottom. Maybe so far we have not talked about what happens here. This is like the area of the instruction. When you do something, you're going to see that. When you do anything, you're going to see that. You see now, when we created 180 element, before I queried, 180 element were being created on this part node. When we created the set one, add one, it told us, or we are given that instruction there. Okay. Okay. So without giving much information, we have defined the geometry, boundary condition, loading, we have meshed. So it means our structure now we can run the analysis. So we need to configure the analysis. To configure the analysis, you just come to job, you double click. You say this is model 1, no job. Continue. Maybe this is general tensile test. Okay, we are going to run full analysis and all that, you say, okay. So when you come to jobs here, you have job 1 already defined. Okay. Then what else? I have not requested for any output. It's an important step, but maybe at this stage, I would not like to do so much on it. But let's see. First, we want to confirm that our model is okay. So you can come here and say data check. Okay. And then as it's submitted, you right click, you say monitor. You want to see whether there are any warnings here. Error. So it's saying it's unable to delete this job. Click. Oh, okay. It's trying to overwrite to save in another file. So what you can do is try to save this work. We have not saved. So you can set your work directory. This one you should have set when we are starting. Set work directory. Now it's saving in a folder called temporary in C. Usually I don't work on C. I usually work on my folder here. Let's say folder E. Then drive E. Then I can say modeling. Okay. Let's say okay. Where is modeling? Modeling E. Modeling. Okay. So now this is my model. I can save as. So I can take it to E in modeling. Modeling. I want to call it tutorial 1 on plate. So let's try to check the data, and we want to see to monitor. We want to see whether there's any warnings or errors in our model. So if you look at this part, if you look here, it's saying Abaqus started completed successfully. Yeah. So our model does not have errors. If there was an error, if there was some undefined, some two parts that are not connected. Usually for a simple case like this one, you might not have those errors. But when you have different parts, and I believe even for your analysis, for your analysis, you might have two parts, maybe for that 4-point loading. When you have those loading points, you define using a rigid body so that they do not deform. But it depends with how you want to apply the load. So it's telling us our model is okay, and we can submit it to analysis. But there is this stage we call the output, because later on, I've not seen you indicate the information you need from analysis. Yes, this is what I was saying. I wanted to check the model without defining, so that now, that step when I want to define the output that I want, if I define wrong output, then I will know the error will be from that area. So sometimes when you know you have already defined your model well, and before you add other steps, you might want to check, so that if there was something that you need to rectify, you can just rectify before you move. You accumulate the errors. So now you come here to defining the output. So the field output, usually if you are not careful, you might output so many quantities, you end up having very large file. If I can go to where I have saved my work, I've saved it in Drive E, I think modeling. This is Abaqus CAE. This is the file that we are working on. It's still small. There is a file that will come here when do analysis. It's called ODB, Output Database. Depending with the quantities that you have requested, you can request stress. And remember, this is 3D stress. Yeah. So you can have the principal stress in all the direction there's here stresses. You can have the von Mises stress. So many stresses requesting, and maybe you're not going to use them. You don't need them for your analysis. Then you might have a very big report. Same case when you use the design software. I find people, when you are compiling report for submission to the local authorities for approval, people are so much impressed with very big document. Yeah. But maybe whatever you are printing, you did not even use it in the analysis. Maybe it's not necessary for you, because we do what we call a minimal, detailed but minimal. I mean analysis. The bare, what can what help us to achieve our goals. So if other parts are not that necessary, you don't have to output them, right? You don't even have to print everything that you get from this, from analysis of any of the software. You need to pick what is necessary. Okay, so when we come here, so field output, you come in the apply load, that's when we define. Like now they want to, you see now we are requesting all these quantities, but I'm not interested in the issue of contact. When I come to forces, I don't want this concentrated forces. Reaction forces and movement are enough. And in fact, only reaction forces. Why? Because it's fixed and I'm pulling. If it was bedding, then movement would be there. Then, so that's why I'm deselecting them. Then in the displacement, translation, don't want rotation. Okay, of course it's fixed here. It might bring in that, but I'm not interested in that. Then strain, I'm just doing elastic analysis. If I did the analysis requesting these plastic strains, there will be a warning. Because in my definition of material, I just defined elastic. So my structure is going to, it will not deform plastic and it will continue erogating indefinitely. So I just want to request elastic strain component. Okay. And then the stresses, maybe the stresses, I can get the stress components. Yeah. So that's what. So you see now I have reduced the quantities that I require. So my output will be small because you are limited in terms of space. Sometimes if you're going to conduct so many models, you find like your hard drive is feeling so much. You end up having a model, one model of one specimen having 20 gigabytes, and so on. Eh? So this is from the output. And again, you can define even for a certain part. If I just want the output for a certain part, I can define it. But for now, let's just for the whole model say, okay. Now, this is the field output. Now, the one that history output, I can define two history outputs. I want history. History output is I want from the initiation of loading all the way to the end. I would like to see how what is the history of that value. If it's about strain, if it's about elongation, I want to see like the load deformation curve. I want to see from the start point 0, the history, the whole during the loading history of the whole structure. I mean of the whole loading period. I want to start that. This is what I'm requesting. And this one I was saying you also need to be careful. You don't want to output so many which you don't need. So in our case here, I'm interested in load elongation. I want to get the reaction, and because it's a pullout, it's a tensile strength test. I want the load, and then I want to get the elongation. I don't want to go to the stress strain for now. So I can request, of course, it's the output is on apply load. So I can request for set 1. Remember, set 1 is set 1 on ed 1. Ed 1 is on this ed. Ed 1 is on the fixed ed. I want to request for forces. I want to get the reaction force. And I say, okay. Then I can create another history output. I call it 2. For ed 2, I want to get the elongation. So I want to get the displacement translation. They say, okay. So I only have requested for 2 quantities for now. Okay. So again, so I believe now the 0 chills you have seen, where that step I had jumped it so that first we could confirm how our model is. So again, it's always good to save. Then let's check again because we have done another addition, and then we monitor to see whether there is any warning or error. Error you cannot run analysis. Warning you can run with a warning error with a warning message. But for elastic and for these simple cases, I don't want you to have a warning because sometimes the warning will come when you are doing plastic analysis, large deformation, large displacement. And the element stretches so much. Abaqus have got the aspect ratio, the preferred aspect ratio. So if the element erogates too much because of we are talking of like a tensile test up to fracture, so you would have warnings here. But for your case, you understand what it means. Yeah. So, but in this case, we are saying there are no warnings, so you can dismiss. So it means our analysis can be run. We have checked, we have applied load, we have specified the output that we need. So I just can come here now and I say submit work. Okay, and I can also, when it's submitted, I can also monitor to be able to see the analysis. Of course, we just defined one test, so it was just the load was applied like. so that's what I was saying in the analysis. In the steps, you may need to define different steps so that the load is not applied suddenly. So it will be incremental. But for now, I don't want to go into that part. So with that, our analysis is done. You can come now here in our job, and now we have moved from modeling. We have come to analysis. Now we are coming to the output. So in the output, if you view results, so this is our structure. You can want to see the deformed shape. Okay. You can visualize. You want to see how it is deformed. You can reduce the animation speed. Yeah. So that you can see, you are seeing how it's deforming. Okay. This shows the S Mises is von Mises stress. I don't know whether at this stage you can comprehend about the stresses. These are the von Mises. Let's say in the visualization, we want to see the elastic strain. So you can see the strain. Of course, at the fixed end here, the values are very high. Okay. Then maybe you don't want to see the principal, you want to see the direction 3, 3. Yeah? Of course, it might be almost be same as the principal. So this is now how you visualize the results. Okay, what else can we see from here? We requested for S. One Mises, you can request the maximum principal, the Tresca, the S33. This is now the stress in the direction that you apply to load, in this Z direction. Okay, the S22, and so on and so forth. Okay, you can stop that. There are many ways of visualizing. You can even do the loop, back and forth, back and forth, back and forth, and so on and so forth. And that's it. So the other part now is now extracting the results that you require. Remember, you can cut this part there, depending on what you want to see. Let's stop this animation. So let's say we want to see one. We want to see the deformed shape and deformed shape, deformed shape and deformed shape. Okay. You want to cut a section, and maybe you want to see the stresses. Cut the section. You want to maybe you want to see in this direction. XY plane or XX plane or XZ plane. You can cut now this one in advanced stage when you want to extract stresses at a certain location. Okay. And then this now XY, you want to extract the XY data. You can click that from ODB history output. ODB, if you go to the folder, the ODB is not yet saved there. Let's see. Okay, not yet. So from the history output, you're going to see a file called ODB or the output database. So let's say you want to get this, continue. We requested for displacement. And so spatial displacement and what? And we requested for spatial displacement only. I think we requested for more than that. History output. Continue. Apply load. Frame all. U1, U1, U2, U2, U3. Okay. Let's say you want to operate on this data. All right. Current session, no ODB. So in this part or this section here is where now we extract the data for load elongation curves. This is where we want to get this type of data. If this is the load, which would be the reaction force F, and then this is the deformation elongation. We want to see how this deformation occurred. Okay. All right, but so far I'm just looking at the chat area there to see whether there is any query or any comment. But I see people are just relaxed. I know it might be quite a mouthful, especially when you're not maybe in your computer. So you may need to sit down and do some of this practice. But I believe after today's short and very brief and very limited. Can I say limited? Because as you have seen, I've tried to avoid so much that you might a lot of a lot of other tools and modules. Yeah, modules. They are called modules. Because maybe at this stage you do not per se need to get so much into that details. Okay. I just wanted to confirm, what did we request? History output. Yeah, we requested only one. That's why I cannot be able to get. Oh yeah, that's why I'm only able to get translation. So we were to define the history output, another one. In apply load, which was I wanted to get. So in the first one, apply load, add 2. So this one, I think we should say add 1 so that you're not confused. And this is when now I want to get the forces, reaction force. And then I create another one for history 2. I want to get for add 2, I want to get the displacement. Yeah. And because our model, that's why I was doing a simple model with very few elements that our analysis can run quickly. Okay, so I have just resubmitted the analysis. And I believe it's completed. And you always need to monitor to see that it's completed with no error. Of course, one-step analysis, one increment is not it's not the way you're going to do your analysis. Yeah, I'm just simplifying one. So and now I view results, and I'm trying to get output database. Yeah. Now we have both the reaction and the displacement. And I want to get this reaction. Remember, one is in X direction, 2 is in Y direction, 3 is in Z direction. And we are loading the Z direction. So I need reaction 3, reaction force 3. So I can say RF3, RF3, all the way up to RF3. So I press Shift. I say save as. And save as here now. I get the sum. I call this reaction. Okay. That is the reaction. Then I come for displacement 3, U3, deformation in the Z direction. Then this U3, I say save as, I sum them, I say deformation or erogation. Okay. I dismiss. Then I have created the data. Then I want to operate on this data. What we say, I click that, I say operate on XY data, continue. So you see I have created 2 data sets, reaction and deformation. So what I need to do is I want to plot. So I want to plot, and I want to use this combine. Sorry, I just need to click one. So I say combine, and then I start with the X, which is the deformation, then comma. Usually Abaqus plots in upward down fashion. So you may find here I'm multiplying by -1 times reaction. So, and I say plot expression. Okay. So you see, because we are doing the analysis, we are doing the elastic analysis, it tells us that our erogation, our deformation continues indefinitely. So this is the force displacement curve, right? So if it was, if we had defined the elastic, the plastic material nature, then maybe at this stage here, so we may be having, we would have something like that. Okay. If we have defined even strain hardening stage, we could have now something coming out. So now from the data from your experiment, you can be able to first validate your model. Because usually the numerical model, we validate with the experimental data. Once we see it, we can be able to simulate the result correctly. Then we can be able to use that model to study now other variables, other parameters, maybe changing the length, changing the depth, if you want to introduce different loading, without having to go back now and do experimental analysis. But first, the numerical model have to be validated. So again, from here, you want to have this data. Later on, you may not need to keep on coming here. So you, after you have plotted, you can say create XY data. Sorry, is it create? No. Yeah, save as. Let's say data 1. Wait, no, not data 1. Let's call it load deformation curve. Okay. Now I can come here. I say tools, XY data. Can say edit, load deformation curve. I have this data here. You see, I only have 2 points. So I can plot it, copy. Then I go to my working plate here. I create an Excel worksheet. So because this is how you shall be doing your analysis, and I hope that with this brief introduction, what you're going to understand in your practicals, then in 5th year, we are going to see people doing numerical analysis in their project. So now you save data, you have extracted it from finite element analysis, and so you save it here. If you want to do other plots and all that, then your data will always be safe. You don't have to go back to Abaqus. When you are doing now your presentation, you can always come here and then you take screenshot of these images, and then you can show people the distribution of the different stress, strains, and all that. So that's all about Abaqus analysis, a simple and I believe a quick introduction to Abaqus finite element analysis. And I hope that you're going to practice on this so that now you can be able to move on to more advanced cases. So that's the end from my side today. And for the 4th year student at a graduate JQuat, this is the last lecture. But I want to calculate a culture of always being found online. So in as much as that our classes are done for now, but every Wednesday in the morning, I'll be having a live stream, trying to answer different questions and also connecting with you guys. So if you have time, you can always log in, but it's not a matter play. Again, always be liking the videos. Once you like the videos, like now you should have liked all the videos in my channel so that they will be recommended to other people by YouTube, because the more engaging it is with the audience, the more it will be suggested to other people and the more it continues growing. So liking, sharing, commenting, leaving your comment. Some people ask me questions via email. It's okay, but if your question doesn't have figures or it can be explained in writing without having a figure, just leave it in the comment section here. That way, apart from benefiting me in terms of the channel growth, also it helps other students. Somebody will see, oh, this question was asked. How was it responded? All right. So thank you, and I'm glad that you've been have been having a team of over 50 throughout. It was an option class, and I like it. So thank you. Go do your practice, and if there are any queries, let me know, and we shall look into them. So unless if there is any question, you are free to leave. And thank you. Could you put a timestamp on this video before you upload it, sir? Oh, it's too long. Okay. By the way, I should do this to all live stream, because again, live streams are good when you want to understand concept. But during revision, maybe you want to go to a specific part. Okay, I'll do that. It's already uploaded. Yeah, it's already, you are watching it on YouTube now. So what I will do, I'll edit. The challenge with live stream, there are some parts you cannot edit. If we make a mistake at the starting, like that's why you always find I try to log in immediately and start speaking. YouTube had a feature whereby you could trim the video at the start of that, but they have removed it. So there's a video, I don't know which lecture, whether it's lecture 5 or 4, where there was some silence because I was on mute. So that first part we cannot be able to remove. Okay, and by the way, I have also made, I think last week I made a tutorial, this week I made a tutorial. You look at the examples that I have given you, I think for beams. Now I believe we have solved them, apart from just one. So you can look at them. It's one is 8-minute video, another one is 14. And that's okay. I hope they will help you to understand the concept. And I believe that throughout that semester that we have been together, you have been able to understand some concept that you carry on into your future life as you practice as engineers. Of course, I'll continue adding more advanced courses in finite element, because I also teach this course to master students. So master students, they don't cover these basics, they start here. So they start here, now we go to the detailed finite element methods. Okay, thank you. Any question, you can leave it there, but because of time factors and all that, I want to end this stream now. Maybe you have another class. I want to end this stream now, but you can always leave your comment there and we shall look at it later on. Bye-bye. God bless you. That's all for today.